Welcome to Differential Equations, section 3.1. In this section, we're basically going to do linear algebra. But it's not like real linear algebra. It's going to be like if linear algebra was a person and differential equations was a person. This is like differential equations sneaking into linear algebra's house and stealing all those cool things. So we're going to learn a lot of techniques without really learning why, or how to expand them into bigger things so that we can just use them for differential equations and get back on our way. We're not going to work hard to earn them. We're just going to steal them, okay? So the first thing we're going to take from linear algebra is the idea of a vector, but you guys should have already known about that from Calc 3. So here, this is like a vector valued function, just like we would have in Calc 3. And this capital A is a matrix, which is just, in this case, it's a 2 by 2 matrix, 2 rows, 2 columns. And so that makes 4 numbers. Now, matrix multiplication times a vector works like this. You do row times column to get one entry. So row times column gives you AX plus BY, and that's one entry on the top. And then row times column, CX plus DY. So that's a vector with 2 components now, one component and the second component. Okay? And so we're using that idea. If X and Y are functions, then we can think of this as two functions there, 2 new functions that match over here what our differential equation is going on. Okay? So now if I think of my 2 functions, X and Y, as, and I'll put the little arrow over it like we did in Calc 3 of T equals a matrix times, so X prime of T equals X of T. Okay? Now, there's a lot of things to know about matrices. So we call A a coefficient matrix. Right? Coefficient matrix. Now there's certain things about matrices that are nice. We like matrices that have inverses are great. So an inverse of the matrix is the matrix that when you multiply that matrix, so A, B, C, D. Now, if I multiply this matrix by the matrix with the scalar 1 over AD minus BC times the diagonal swapped and the off diagonals made negative. And what I'm going to get is what's called the identity matrix, which will have a 1 here and a 1 here and a 0 and a 0. So let's do this. So let's move the scalar out front of everything. Okay. And then a row times column, so AD minus BC. Okay. Row times column, so CD minus CD, that's 0. And then row times column, that's negative AB plus AB, so that's 0. And then row times column, which would be negative BC plus AD. Well, the way scalars multiply through a matrix is the scalar multiplies through every single entry. So then 1 over AD minus BC will just be 1, 0, 0, 1. Okay? This is called the identity matrix because the identity matrix functions like a 1 when you multiply it times vectors. So 1, 0, 0, 1 times the vector xy equals the row times column, that gives you x, row times column gives you y. So, oh, you can't see that, sorry. It functions like multiplying by 1 because row times column gives you x plus 0y, and row times column gives you 0 plus y. So that's just y. So the identity matrix times vectors gives you the vector back, just like multiplying by 1 does. So that's why we call it the identity. Okay, and so the inverse is a matrix that when you multiply a matrix by it, you get the identity. Just like how the inverse of multiplication is division. So it's like, instead of multiplying by 2, it's like multiplying times 1/2. Okay? So that is matrix inverse. Okay, now the determinant. This part, when you do the inverse, this part right here is called the determinant. Okay? And you need it to be not equal to 0 in order to take the inverse, otherwise you're dividing by 0, and you can't do that. Okay. Now, linear independence. Okay, so I think we're mostly working in the 2 by 2 case here. So say you have two vectors. If their determinant's not equal to 0, then they're linearly independent. Okay, we're just going to use that. There's this broader notion of what linear independence means that will make so much more sense if you listen to that, but you have to take linear algebra to get that version. For this version, it's just that if you have some vectors, if you put them in as columns, then, and you take the determinant, if it's not equal to 0, then they are linearly independent. If they're not, so a linear combination, so say I have 3 vectors, then they're not, these ones are not linearly independent because one vector is a linear combination of the other two. Some constant times the x vector plus some beta times the y vector gives you the z vector. So that makes it linearly dependent, these 3 vectors. Okay, so you could write this that way. Okay, there's also these vectors right here. Those are called the the standard basis. So in Calc 1 we use I and J, and the better thing to use is E1 and E2, because if you happen to go into have more, if you happen to have more systems of equations, so if you have like 3, 4, 5 equations, then you run out of letters if you do IJK. So to the more formal, not formal, the more sophisticated way is to do E1, E2, E3 instead of IJK. All right, standard basis. Well, now here's some vectors, 2, 1, 2, 3. Okay. Now, let me look at this one. So then if V is 2, 1, and V1 is 2, 1, and V2 is 3, 2, so then if Z is -5, -4, so Z can be written as 2 times V1 minus 3 times V2. So the coordinates of Z are 2, -3, 2, -3 with respect to these vectors, which are called a basis. Oh man, we're just flying through linear algebra terminology right now. So we're sticking to 2-dimensional, and that helps hopefully. So these 2 vectors, because they're linearly independent, form a basis of 2-dimensional space, because they also span all of 2-dimensional space. Any vector can be written as a linear sum of them. And so then we can write things as coordinates in terms of this basis instead of the standard basis. So it's, Z is like -5, -4 according to the standard basis, and it's 2, -3 according to this basis. Okay? Now, let's do some fun matrix multiplication. Activity 3.1.1. Okay, so first I'm going to calculate some matrix multiplication, A times B and B times A. So A times B, that's equal to 5, 3, -6, 4. And B is 2, 3, 1, 2. Okay, so then that's 10. So 5 times 2 is 10, plus 3 times 1 is 13. And then 5 times 3 is 15, plus 3 times, maybe I'll do this a little slower for those of you who have not had any algebra. So we'll do it a little slower. So 5, you do row times column. So 5 times 2 plus 3 times 1. and then row times column, 5 times 3 plus 3 times 2, row times column. So then bottom row times first column. So -6 times 2, row times column, plus 4 times 1. And then -6 times 3 plus 4 times 2. Okay, so notice how like row times column, row times column, row times column, row times column. Okay, now simplify. So then that's 10 plus 3 is 13, 15 plus 6 is 21, -12 plus 4 is -8, -18 plus 8 is -10. Okay, so that's A times B. Now B times A, that's opposite 2, 3, 1, 2 times 5, 3, -6, 4. Okay, so again, we'll try to go a little slower for those of you who haven't done the algebra. So then rows times columns, 2 times 5 plus 3 times -6, and then row times column, 2 times 3 is 3 times 4. And then bottom row times first column, 1 times 5 plus 2 times -6. And bottom row times right column, 1 times 3 plus 2 times 4. Okay, so we've got 10 minus 18 is -8. And then 6 plus 12 is 18. And then 5 minus 12 is -7. And then 3 plus 8 is 11. Now notice something. I multiplied two things in opposite orders and got totally different things. That's something that happens with matrices. And if you're only used to doing arithmetic with numbers, that could be kind of crazy, but it is definitely true. So that's matrix multiplication. All right, now part B. Oh boy, we got to find a bunch of inverses. A inverse. So A inverse equals 1 over A times D is, so 1 over, so here's, where do I have A written down? A is right here. 1 divided by this diagonal minus that diagonal. This diagonal is 20 minus negative is plus, so plus 18 over, and then swap the diagonal and make that off diagonal negative. Then negative is a positive. Okay, so simplify that fraction. 1 over 38 times 4, -3, 6, 5. No need to, oh, I'm sorry, you can't see that. Okay, so 1 over first diagonal minus the second diagonal, but the second diagonal is negative, so negative is positive. And then simplify that. But then you could move this into everything, but why would you? I mean, let's just keep that fraction out here so we don't have to write a fraction once. Okay. Now let's do negative B inverse. B inverse. Where is B stated? B is stated up here, 2, 3, 1, 2. So one diagonal. So the first diagonal is 2 times 2 is 4, minus the other diagonal. And then we swap the diagonal entries, but they're the same, so it doesn't matter. And then off diagonals become negative. So 4 minus 3 is 1, so you can just forget about that. 2, -3, -1, 2. Why can you forget about it? Because 1 times anything is just that thing. All right. AB inverse and then B inverse times A inverse. Oh man. Oh. Matrix multiplication by hand, like a pioneer. All right. AB inverse equals, so here I have AB way up here. You can't see it anymore. But you should have tried this before watching this video. So hopefully you have it. So 13, 21, negative 8, negative 10. So 1 over the first diagonal, 13 times negative 10 is negative 130. And then minus a negative 8 times 21 is 168. So plus 168 times, and then diagonal entries switch, and off diagonals become negative. All right, so let's simplify that fraction out front. And we get 38 1 over 38 times negative 10, 21, 8, 13. Coolio. Okay. All right, do I have room to fit the last part? B inverse times A inverse? I think I do. So B inverse is 2, negative 3, negative 1, 2 times, I'll move the fraction out front, times 4, negative 3, 6, 5, and then so remember, don't forget that fraction. And then row times column. I'm just going to do some of the arithmetic in my head now. Hopefully we don't mess this up. So 2 times 4 is 8, minus 3 times minus 18. 8 minus 18 is negative 10. And then 2 times negative 3 is negative 6. Negative 3 times negative 5 is negative 15. So add those together, you get negative 21. And then negative 1 times 4 plus 12 is positive 8. And then negative 1 times negative 3 is 3. Plus 2 times 5 is 13. Look at that. And those are both the same number, and it's not a coincidence. So if you look here, inverse does a weird thing. You need to be really, really aware of this. The inverse of A times B is not A inverse times B inverse, it's the swap. So when you move inverse through, it swaps the order of multiplication. And that's important because in matrices, A times B is not equal to B times A. Similarly, A inverse times B inverse is not equal to B inverse times A inverse. But when you have AB with inverse, move it through, it swaps the order. Important, important, important. Don't forget it. Okay. Now we got to find all those determinants. But I already know them because, well, do I? Let's see. I already calculated A inverse and B inverse, so I know those determinants. So A inverse, we already found that determinant to be 38. Determinant of A was 38. And we found the determinant of B to be 1. And the determinant of AB that is equal to determinant of AB is, well, let's find AB. 1 over 38 times that thing. So then equals, oh wait, where am I? AB. So A times B was 13, 21, negative 8, negative 10. So 1 over, already found that when I found AB inverse. It's also 38. And determinant of A inverse is A inverse is 1 over 38 times a thing. So 1 over 38 times 20 minus 4 times 5 is 20, and then minus to plus. +20 plus 18 equals 1/38 squared times 38 equals 1/38. Okay, why did I make the fraction of those out front 1/38 squared? Well, think about it. So this is 2 of the entries multiplied together. They would both be over 38. And this is 2 of the entries multiplied together. They would both be over 38. So move those over 38s out, and you have 2 of them. 2 1/38s. Okay? That cancels out with that 38, and you get 1/38. Okay. That makes sense? It's kind of a trick of the trade that I just did there. But if you really were to, instead of, you try to do this, determine A inverse, if that didn't make sense to you, take A inverse and put that 1/38 into each element of the matrix. And then take the determinant, you'll see you'll get 1/38. Okay, D. Oh, there's X and there's, okay. Okay, AX. Matrix multiplication by hand is making me tired. All right, AX. So that's equal to 5, 3, -6, 4 times the vector 1, 0. So that's equal to 5, and then -6. This is the first column, all right? And then A times Y is 5, 3, -6, 4. Y is 2, -1. So then 5 times 2 is 10, -3 is 7, -6 times 2 is -12, -4 is -16. Oh, you can't see that, I'm sorry. Okay, I'll say it again. So row times column, so 5 times 2 is 10, 3 times -3 is -3, so 10 minus 3 is 7. And then row times column, so -6 times 2 is -12, 4 times -1 is -4, add them together, you get -16. Okay, now y transpose times x, so y transpose, that little t there, right? Y transpose is 2, -1. 2, -1 times x, which is 1, 0. So row times column is 2. Okay, and then x times y transpose is equal to 1, 0 times 2, -1 equals, now here we do row times column. So there's only one row. There's one row there. Sorry, there's 2 rows and 2 columns. So row times column is 2. Row times column is -1. Row times column is 0. Row times column is 0. Okay. That completes activity 311.